Hi everyone, this is my first video on this YouTube channel, and today I'm going to share with you the history of machine learning and in particular deep learning in recent history up until LLMs being introduced and GPT-4. So my background is I have an MSc in machine learning taught in conjunction with Google DeepMind, and I run an AI company called Genie AI. And yeah, I just hear a lot of people talking about machine learning, and I'm sure that you're probably a bit bored and tired of hearing about LLMs and GPT-4. But many of those people perhaps don't have the background that I'm kind of lucky enough to have. And so I almost feel compelled, if you will, to share the recent history of machine learning as I've experienced it in the last 10 years. And it must be said that 6 years ago, I wrote my thesis in generative AI, in particular, an algorithm called GANs. So it's been fascinating to see that progress up until the stage where it is today. But let's hop right into the quick history, and hopefully this gives you guys a useful kind of backstory into how we got here and a good amount of technical information, but also keeping things high level and interesting, so it's hopefully digestible. So I think we can start in the kind of pre-2010 era, and this is when the concept of deep learning, neural nets, were just starting to be used. But according to GPT-4, I actually asked it what it thought that the history of machine learning actually was. And I must say GPT-4 wasn't too accurate. It had some of the kind of key points, the highlights, but not all of them. But here it said that traditional machine learning techniques dominated the landscape, so SVM, random forest, and so on. So these are machine learning techniques because machine learning is simply a mathematical model that learns from past data. However, they're not neural nets, and in particular deep neural nets, which are simply neural nets with many, many layers, which is the predominant algorithm that dominates machine learning today. And in fact, large language models are a specific type of neural nets in most circumstances today, although in the past they didn't have to be. So that was kind of pre-2010. Let's go on. And I wasn't so satisfied with the history that GPT-4 came up with for machine learning when I asked it. So I had to add in my own flavor here. And in particular, GPT-4 missed out the critical MNIST dataset, the famous MNIST dataset. So what was MNIST? Well, you can see the background here, which is a lot of handwritten digits. And this was first released in 1994 by a chap called Yann LeCun, who is now known as one of the godfathers of AI, and in no small reason because of this particular release and dataset. But back then, as you all know, machine learning models require large amounts of data to work well. And back then, there simply wasn't that amount of data, and especially not in a structured form. So Yann and his team painstakingly created many handwritten digits and labeled them in terms of what digits they actually are. And after that, many researchers trained models of all kinds, trying to predict what those handwritten digits actually are. So you can see here, maybe this in the bottom left, or even here, the 7 could be a 9 maybe. Most of these are quite well written, but there are versions which are a lot worse written. And I slightly have nightmares looking at this because for my machine learning degree, we had to build neural nets from scratch to predict these digits. So I just have visions of seeing them in large pixelated form. But anyway, let's go on. This is a Wikipedia shot of some of the models used to predict the handwritten digits in MNIST. And it's quite interesting actually, because if you look at the original models, they were non-neural nets, meaning what GPT-4 has termed as traditional machine learning methods. I don't know if traditional was really accurate, but they're algorithms which are not based on neural nets. And then here, this is actually in about 2002, if you can see where it says DNN in the middle, deep neural network, 2-layer, 784, blah, blah, blah. So that was in about 2002. And then the first convolutional neural network was introduced, I think, around 2016 or 2014. So that kind of gives you quite an interesting view of the history of these sorts of algorithms. And ImageNet was also released in 2019 because this was a massive dataset of images, because once again datasets were so hard to come by in the scale and structure required by machine learning back in the day, especially because we required the data to be in supervised learning format, meaning that you need an input and an output, because the model learns from the pairs of inputs and outputs to predict a new output given a new input. Generative models these days don't really work like that. I'll go into that in a future video, but for now, that's what's called a supervised dataset, so a paired dataset of inputs and outputs. But yes, ImageNet was released, and computer vision really started to excel during this time and really made deep learning become a thing, because obviously we have the major advancements in compute power which really helped deep learning, which are once again large-scale neural nets, perform well. We had GPUs from NVIDIA and so on. But in terms of the data, images were easier to work on because images are made out of pixels, and pixels can be easily read by machine learning models because you can simply reduce an image to a three-dimensional vector of red, green, and blue. Or was it yellow? I can't remember. In either case, it's vectors of values which represent colors that ultimately build up the picture. Hopefully that's not too technical for this video. But given the fact that you can reduce images to numbers, and numbers can be put into mathematical models, that's why deep learning started to work really well for images. And for words, it was a lot harder actually for NLP, because images and colors are continuous. So there's a continuous scale from red to blue. But is there a continuous scale from cat to dog? Maybe, but that would be a strange world. So many models were developed on this ImageNet dataset, and here are a few famous ones. AlexNet by Geoffrey Hinton, who is now known as one of the other godfathers of AI. It's a shame we don't have any godmothers. Maybe we do, and we need to celebrate them more, but that's a different story. In 2014, Google's Inception came out, which had, I can't remember how many parameters, but it was something like 60 million. And at the time, everyone was like, whoa, this model's massive. And that's why they called it Inception, because it was kind of crazy. And everyone was just thinking, there's no way we can beat these massive Google models. But of course, now the models are even bigger, by a factor of 1,000. And Microsoft's ResNet came out, which had some interesting architectural developments. And this is an interesting point in terms of it's the architectural developments that really make the breakthroughs in machine learning, although the inexorable advance of compute power and data, structured data, makes sure that machine learning progresses no matter what. for better or worse. So going on then, after 2010, in 2014 we had Word2Vec, which was an amazing invention and breakthrough, because as we just discussed, machine learning on images, known as machine vision, was working really well. But machine learning on text data, on NLP, was struggling a bit, you could say. I mean, maybe not struggling, but just not moving as fast as images. But Word2Vec changed everything, because for the first time, you can now convert words to numbers, which can easily be read by machines. That's not totally accurate. There were ways before this to represent words as numbers, for example, the bag of words method. But Word2Vec put words into what's called a high-dimensional space, which is a mathematical space that can represent the meaning of words, quote-unquote meaning, in a highly accurate way relative to all the other words in the corpus of text. So you can see here an image of the words king, man, and woman being put into these squares, which really represent vectors of numbers. A vector is just a row of numbers. So that was really cool, and people used this concept of word embeddings to ingest corpuses of text, and another algorithm called GLOVE was used a lot, created by Stanford after Word2Vec. And 2014 was a big year for machine learning, if you think about it, because GRUs were also invented. So GRUs are a variation of RNNs, and RNNs are a type of neural net, a type of deep neural net. And back then the problem was this idea of vanishing gradients, where if you try to take a neural net and you add many, many layers to make it a deep neural net, yes, it gets more accurate, but the downside is as you pass the data through it, since it's very deep, the learning or the gradients vanish over time, especially with large sequence lengths or large data sets. And so RNNs stand for recurrent neural nets, because it's a way of creating recurrence, of folding the neural net on top of itself. And in doing so, you retain long distance memory of the learning. And so LSTMs, for example, long short-term memory neural nets, are a type of RNNs. And so are GRUs, which LSTMs were introduced many, many years ago, but GRUs more recently. And they just trained in a bit more of a stable way compared to LSTMs, because training models historically was quite hard. It's getting easier and easier. But I remember this quite clearly, because when we were doing our MSc machine learning course with Google DeepMind, they made us hand code LSTMs and GRUs using TensorFlow 1.0, which was pretty terrible, which is a Python framework. And I equally have nightmares of watching that. Although it was very interesting, because the GRU training regime was a lot more stable than LSTMs. So that was pretty cool. And this image is just a module of a GRU, but we won't go too deep into that just now. So let's go on. I hope you're enjoying the crazy backgrounds in this video as well. But yeah, this incredible year for machine learning, 2014, then brought us sequence-to-sequence models. And this was a big breakthrough, because this is one of the foundational pieces, one of the clues that led us to OpenAI's GPT models and transformers as they are today. And so the concept of sequence-to-sequence is really simple. All it is that you're taking arbitrary input length of data, an arbitrary sequence, and you're returning a sequence of data. So For those of you who are in finance or economics, you might know this as autoregression. But the reason it's fascinating for us as ordinary people is because, in a way, you can represent almost anything as a sequence. Think about it. Life is a sequence of time steps. So this video is a sequence of seconds, or a sequence of image slides. What you tell someone is a sequence of words. A movie is a sequence of scenes. And so the expressive power of sequences is quite incredible. And that's actually one of the real secrets behind why LLMs and the GPT models have become so big. It's not actually the power of them, it's the flexibility of the expression of the model. So you have encoder and decoder models, or just encoders or just decoders. I won't go into that right now, but that was a major breakthrough in my opinion. And then another major breakthrough, everything happened in 2014. So machine translation was really doing well at this point. So Google Translate, for example, started to perform really well. And attention is really an architectural mechanism inside neural nets where you take two vectors of data and you dot product them. In simple terms, you just take two chunks of data and you multiply the items in the chunks together. So what's the point of that? Well, it solves this problem of it helps the model to learn across large data sets. It helps the model to focus on the right areas at the right time and therefore learn by producing the right gradients that don't vanish across time. That was really vague, but essentially attention is a way to focus on the right parts of the data at the right time so the model becomes more accurate and performs better. As you can see here, there are different types of attention, global attention, local, and so on. And we'll go on to another type of attention, which was also groundbreaking very soon. But remember this, because attention is another one of the clues to why the GPT models are so famous right now. So in 2017, we had a huge step, which was the transformer. And the key aspect of the transformer that makes it a transformer is self-attention. So this paper was created by a chap called Vaswani et al., and his name is emblazoned on my memory forevermore, because this was really the foundation that brought everything together in order to create LLMs as they are today. Because LLMs as they are today, by the way, LLM stands for large language model, are based on transformer models. They're all transformers. GPT-1 to 4 are transformers. So is BERT and other transformers. And there are loads of them, long former, short former, Roberta, BERT, many more. So why are transformers so amazing and powerful and accurate? It's quite impressive because transformers are not a complication on previous models. They're not a whole new architecture that's really complicated and advanced. In fact, they're really quite simple compared to what was up until 2017 state of the art for most cases, which was recurrent neural nets, RNNs, as we just talked about. So transformers, as it says here, dispensed with recurrence and convolutions. Convolutions were from CNNs, convolutional neural nets, which were often used in image learning. But transformers were kind of like, we don't need any of that stuff. All we need is self-attention. And hence this paper was called Attention is All You Need. And all self-attention is it's a type of attention which dot product which multiplies every single item in two vectors together. And by doing so, what happens is you're able to attend to every item in the data, and thereby creating this mixing effect across the data, which increases accuracy massively. And you then stack those self-attention heads to create what's called a multi-head attention mechanism. But that doesn't matter too much. All you need to know is that self-attention is the key aspect that made transformers, or makes transformers, and transformers is the underlying model which GPT models are based on. Meta's Llama models, all the current LLMs are almost all of them are transformers. So hopefully that gives you some understanding of the importance of transformers in today's current state of machine learning. So of course we then had in 2018 GPT-4, and the most interesting part of language models at this stage was the fact that people realized, hey, we don't need to train everything from scratch. In fact, we can just take a pre-trained model, a model that's already been trained on past data, and then just continue the training a little bit more on some specific data or on a specific task. And in doing so, the pre-training increases the accuracy for the current task that you need the model for. So this was the era where everyone wanted one model per task, or you had models that were specialized for specific tasks. And the predominant theory in machine learning at the time was just having specialized models, and many of them. It was around this time actually that I started to really analyze transformers, and I became amazed because I realized that they were sequence to sequence, meaning that you could do almost any task using this sequence to sequence approach. And I went to NeurIPS 2019, which is the premier deep learning conference in machine learning, and it was an amazing time because everyone was experimenting and seeing how these models are performing, and really breaking boundaries and what could be done. And I could see at the time that these models could be used for anything, but they were still being used for very specific tasks. And I do recall telling our machine learning engineer at Genie, we should build one massive model that can do everything. But that was blasphemy at the time because the prevailing theory was one model per task. But anyway, we go on. So another transformer that was very famous at the time was called BERT, which stands for bidirectional transformers. And this was essentially a type of model that looked at not only the starting context. So the way these transformers work is they take an input sequence and they predict the next token. Next token meaning the next item in the sequence. So let's say I give you 1, 2, 3, 4, 5. It will predict 6, right? So it's really that simple in most cases. And so the way BERT worked is that it would take 1, 2, 3, 4, 5, but it would also see 6, 7, 8, 9, 10 in its training data. And then when it gets to test time, and you give it 1, 2, 3, 4, 5, it's more accurate at predicting the whole next sequence because it's seen the whole next sequence in its past data or something similar. That's what's called bidirectional. And BERT actually outperformed GPT-1 in most circumstances, and even GPT-2, I believe, if my memory serves me well. So most people tended to use BERT or some derivative of BERT, like Roberta, and so on. But yes, GPT-2 came out with a massive 1.5 billion parameters, trained on 8 million web pages, and performed even better. And there was this kind of competition between GPT-2 and BERT. And then the major breakthrough was GPT-3, which wasn't really a breakthrough in my opinion, because it had almost the same architecture as GPT-2, just some optimizations to help it train easier and more efficiently. And the discovery, if you like, was when you ratcheted it up to 175 billion parameters. And remember, back when we were talking about Inception 10 years ago, or was it 6 years ago compared to 2020, I think they had around 60 million parameters. Correct me if I'm wrong, someone who's watching. But now, we reached 175 billion parameters. And in fact, Google were training 1 trillion parameter models not long after. But they were sparse models. But anyway, yes. So at this scale, what people realize is that the model started to generate human-like text. And like I say, these models are generative, meaning that they take an input sequence and they produce an output sequence. They generate an output sequence. And that can be anything. It can be text. It can be finishing off a sentence. It can be the next most likely words after the prompt that you type in. And that's how GPT-4 currently works, or ChatGPT. So, yeah, and then, of course, we go on to 2022, getting very close to where we are today in 2023. And what really differentiated GPT-3 to GPT-4, what really created ChatGPT, was this intermediate stage of instruct GPT. And what OpenAI realized, and again, it's funny because OpenAI haven't done anything clever throughout their history here with the GPT models. Not to say there aren't many great people working there, but there's no architectural innovation here. All they've done is they've taken the basic transformer, they've turned it into a massive model because they have massive amounts of money to put into compute power. And then they found, it started to perform almost like a human, if not better. And then they thought, okay, well, we have all this data of people typing in prompts and instructions to GPT. And these instructions are not like the NLP machine learning benchmarks that we use to judge its accuracy and to train the quality of the model. So why don't we get a whole bunch of humans to label up how to respond to how our users are asking questions. And they called this concept alignment, which I find really funny because it's become a buzzword, but all it is just listening to your users and building a product that your users actually want, as opposed to some, technical mathematical model. And so that was the idea of instruct GPT. And again, they created this concept of RLHF, reinforcement learning from human feedback, and gave it a name, and that became a buzzword, but it's nothing. It's nothing new. Reinforcement learning has been around for 50 years or something, and all they're doing is reinforcement learning on human labeled data, which doesn't need a whole name or category in itself. It's just the same old reinforcement learning on, the same old humans labeling data. So admittedly, they did use a specific policy gradient algorithm for the reinforcement learning called PPO, but all that is it's just an efficient method of doing policy gradient. So again, nothing too special there. It's an algorithm that's been around for a long time. So yeah, that led to GPT-4, and apart from instruct GPT, one of the major efforts that went into GPT-4 was just making it a lot more safe for users to use. They reduced responses to malicious requests by 86%. That obviously leaves 14% that GPT-4 still responds to. And they added some extra abilities such as a version of GPT-4 that can work with large context lengths. And the context length limitation is because of the self-attention being a function of n squared, meaning that the amount of data you put in each sequence has to be multiplied by itself. So each item in the vector multiplied with each other item in the vector, meaning that it's n squared, so n being the amount of data in each vector, squared multiplied by itself. Which means that if you're increasing the context length, the amount of inputs, or the input length that you put into a model, then you're squaring the complexity. But I imagine I'm going too far right now. I can go into that and explain that in another video in a much easier way. But this brings us to GPT-4, which is where we are today. And in subsequent videos, I will share with you where I believe we're going to go next. Because now that we know the history, we can start to see the patterns and we can start to draw conclusions about what we will see very soon. So if you have any questions, just drop them in the comments. I will respond. But otherwise, I hope you enjoyed my first video. Thank you very much and see you all very soon. Ciao.